Now in this video we will discuss about the properties of haloalkanes. The properties can be physical and chemical. First we will start with physical properties. In physical properties we will mainly discuss solubility, then boiling point. And first is solubility. Solubility means if any compound forms hydrogen bond with water, then it is a water soluble, otherwise it is not. So haloalkanes do not have in this haloalkanes, if they are fluoroalkanes, then only can form hydrogen bonding with water. Otherwise all other haloalkanes have polar bonds, so they are not able to form hydrogen bonds with water, so they are less soluble. But due to the polar bonds, that is dipole-dipole attractions, they are soluble to some extent. So these are soluble in water, solubility is low, and they are soluble in organic solvents. So now the boiling point is again in boiling point we see their bonding between the same molecules, and in this again and low temperature can easily break that bonds, and the boiling point is low. So haloalkanes have low boiling points due to the lack of hydrogen bonding. Now next is polarity. As we have already discussed, they are polar due to the presence of halogen atoms, and in this chloroalkanes will be more polar than bromo than iodo because of the difference of electronegativity. Cl is more electronegative than Br and than I. So chloroalkanes are more electronegative, they are more polar, and iodoalkanes are least polar. So now comes the chemical properties. In chemical properties we will be discussing nucleophilic substitution reactions, then elimination reactions, then reaction with metals, then reduction, and last is rearrangement reactions. Next is rearrangement reactions we will be discussing in the first is in haloalkanes the bond is polar, so the more strong nucleophile can replace the already present halogen. So in this nucleophilic substitution reactions take place, and so first we start with nucleophilic substitution reactions, that is in nucleophilic substitution reactions halogen atom is being replaced by a nucleophile if it is stronger than the halogen. So stronger nucleophiles replaces the halogen and they give substitution products. So haloalkanes undergo nucleophilic substitution reactions as nucleophile attacks and it replaces the already halogen present, and so we get nucleophilic substitution reactions. There are a large number of nucleophiles which can replace the halogen. We have 12 to 13 reactions in which nucleophile, it may be OH, it may be CN, there are a lot of nucleophiles, NO2, ONO2, all can replace halogen. This we take up as first is when it is treated with aqueous potassium hydroxide or moist silver oxide, then we get alcohols. X is replaced with OH group and we get alcohols. So when haloalkanes are treated with aqueous potassium hydroxide or moist silver oxide, then we get alcohols as the main product. Taking up an example, that is CH3CH2Br. In this Br is replaced with OH group and we get alcohols. Similarly, if we treat it with potassium cyanide with KCN, then we get cyanides, or these are also called nitriles. That is X is replaced with CN group and we get RCN, that is nitriles. Now if we treat it with silver cyanide, so if we treat with potassium cyanide, then we get cyanides, but if with silver cyanide, then we get isocyanides, RNC. So this is because KCN is the ionic bond, has the ionic bond, thus has a covalent bond, AgCN. So we get this in first case cyanide, in the other case isocyanide. This we will discuss in the reasoning question next. And now taking up a particular example, we get with AgCN we get CH3 CH2NC, that is ethyl isocyanide. So next is, if we treat it with AgNO2 silver nitrite, then nitroalkanes are formed. But if we treat it with potassium nitrite, then the product is different and it is ONO, that is alkyl nitrite. But with AgNO2 nitroalkanes are formed, with potassium nitrite alkyl nitrites are formed. So then if we treat with sodium NaSH, then SH replaces the halogen atom, that is we get RSH. Now is this, if we treat with aqueous NaOH, we get alcohols. Now we are treating with NaSH, that is instead of oxygen we have S, and for this we use thio, so we get thioalcohols. RSH is thioalcohols, in which sulfur is used instead of oxygen. Now if we treat with haloalkanes with NaOR, then we get OR group is introduced, that is X is substituted by OR group and we get ether group. So taking up example, CH3CH2Br with NaOCH3, we get this methoxy ethane, this is a ether. So with sodium alkoxide NaOR, we get ethers, or it is the formation of ethers. And this method in which we prepare ethers is called Williamson synthesis, that is the reaction in which alkyl halides reacts with sodium alkoxide in the presence of to give ethers, that is this reaction is called Williamson synthesis. This reaction is also important for naming reactions. And now if we treat with ammonia, haloalkanes with ammonia, we get amines, it is primary amines. If we treat with primary amine, then we get secondary amine, then tertiary amine, and so on. So alkyl halides with ammonia give amines, and then with, if silver salt of acid RCOAG, that is silver salt of acid, then esters are formed, that is RCOAG, plus haloalkane gives esters RCOOR. Taking up a particular example, that is instead of R we use CH3, then we get silver, that is silver acetate, with CH3CH2Br, then we get CH3COOCH2CH3, that is this group replaces silver and we get ethyl ethanoate plus AgBr. So next is, if we treat with sodium azide, then we will get RN3, that is alkyl azide, that is with sodium azide alkyl halides give alkyl azides and sodium halide. And if we treat it with alkenyl group ALKYNYL, here should be YL, alkenyl group kinds. So we have many nucleophiles which can replace the halogen atom. So it and all involves nucleophilic attack, that in all the reactions nucleophile first attacks. So these are the nucleophilic substitution reactions. Now we can easily explain why haloalkanes give cyanides with KCN and isocyanide with AgCN. So as I have already told you that in KCN bond is ionic, or it is a ionic solid. So in this C and N, that is carbon-carbon bond is relatively stronger than the CN bond. Therefore CN attacks through carbon. It attacks through carbon to give cyanides. On the other hand, in AgCN there is a covalent bond. So only nitrogen is free to form bond, and it gives to donate electron pair and attacks to give alkyl cyanides. So we can see in this example that in KCN cyanides are formed, in AgCN due to covalent bond only nitrogen is free to attack, and it gives isocyanide. And so similarly in case of potassium nitrite and silver nitrite, in this again potassium nitrite gives different products and alkyl nitrides, and silver nitrite gives nitroalkanes. This is again on the basis of the ionic and covalent bond involved in this. And so this is all about the nucleophilic substitution reactions in which the various nucleophiles can replace the haloalkanes.